Good evening, everyone. Welcome to the live interaction session of week 6 of our course Computational Fluid Dynamics by Professor Srinivas Jayanthi of Department of Chemical Engineering, IIT Madras. Myself, Manjunadan, your TA for this session from Department of Applied Mechanics, IIT Madras. So, last week we have seen the in week 5 lectures we have seen about how this discretization or how these finite difference approximations are applied to the differential equation or finite difference approximations have been applied to the differential equations have been discussed in last week. So in this week lectures, that is week 6 lectures, covered the basic concepts of safety such as consistency, stability, convergence, and uh, other uh, basic concepts that are very much crucial for the understanding of CFT or to run a CFT problem. So let's start it with the questions. So in this interactive section, we'll be discussing questions based on the course content followed for the previous week. So I'll be reading out the questions for you, and you can take your time and try to answer the question by yourself and inbox your answers. Then we will discuss about the answers. So let's start with this section. Question one: for the expansion given by the equation f of x plus delta x is equal to f of x plus a into df by dx plus b times d square f by dx square plus c times d cube f by dx cube plus d times d raised to 4 f by dx raised to 4 plus e times d raised to 5 f by dx raised to 5 plus etc. to be convergent, which of the following conditions are needed to be satisfied? So the question is on the basics of differential equation and Taylor series expansion. So the question is on for such a series to be such an expansion to be convergent, uh, what are the necessary conditions should that is to be satisfied? Uh, Conditions are condition 1 small x, condition 2 f to be continuous, that is a function should be continuous. Uh, Third condition, that is f to be differentiable, the function should be differentiable. And the options are option A, condition 1 is sufficient, option B, condition 2 is sufficient, option C, condition 3 alone is sufficient, option D, all the three are necessary. So you can inbox your answers. So answer is option D. All three are necessary. This is our answer. Option D. All three are necessary. So this function f of x plus delta x, this expansion to be convergent, the x should be small enough and f should be continuous and f should be differentiable. So all these are actually from basic differential calculus. For a function f to be differentiable itself, it should be continuous and it should be small one. So from there only these equations are developed. So from in the basic point of calculus view itself, all these conditions should be satisfied for this expansion to be uh, convergent. So our answer is option D. Moving on to next question. This question is on Lax theorem. Lax theorem states that which of the following statements best suits the explanation for Lax theorem? Options are option A, convergence is assured for a well-posed linear initial value problems. Option B, stability is assured for a well-posed linear initial value problems. Option C, consistency and stability are sufficient for convergence for a well-posed linear initial value problem. Option D, none of the above. So, which among the following best suits the statement of Lax theorem? So, to simplify, what does the Lax theorem directly states? Is the Lax theorem is on convergence or stability or consistency? Which of these four factors, which of these three factors does Lax theorem states about? So our answer is option C is the right answer. Lax theorem states that consistency and stability are two conditions that is sufficient for the convergence of a well-posed linear initial value problem. So you should understand that the Lax theorem is about convergence and how convergence is related with consistency and stability. So uh, Lax theorem basically combines consistency and stability with convergence, and that's only for there's also another condition like it is the consistency and stability are sufficient for the convergence of a well-posed linear initial value problem. That is, the problem should be well-posed and it should be linear one and it should be an initial value problem. So initial value problems are also known as IVP in short form. Hope that is understood. Let's move on to next question. Next question, question 3. Wiggles, that is stable spatial oscillations in regions of large gradients, are an indication of what type of numerical error? So there are, as we have discussed, as you might have seen in the videos, there are different types of numerical errors, and which among the following is the reason for wiggles? One, diffusive. Two, dispersive. Three, truncation. All these errors are different types of numerical errors. So, which type is the reason for wiggles in the regions of large gradients? Is it diffusive? Is it dispersive? Is it truncation? Options are one only, that is diffusive only. Option B, two only, that is dispersive only. Option C, one and two, that is diffusive and dispersive is the reason. Option D, all these numerical errors can cause wiggles. So, which among the following options is right? You can invoke your answers. Yes, our answer is option B, that is dispersive error. Dispersive type of numerical errors creates spatial oscillations known as wiggles. Next question, question number 4. It's on von Neumann stability analysis. The question is, the von Neumann stability analysis is restricted to which of the following? First one, linear initial value problems. Option. Second one, periodic boundary conditions. Third one, linear boundary value problems. So, and the options are option A, one only, that is only two linear initial value problems. Option B, 2 and 3, that is one Newman stability analysis can be applied to periodic as well as linear boundary conditions. Option C, that is 1 and 2, one Newman stability analysis can be applied to linear initial value problems and periodic boundary conditions. Option D, all the above. So the one Newman stability analysis can be applied to all the three. So you can inbox your answers. You can think what is one Newman stability analysis and uh, which of the following problems can be subjected to uh, von Neumann stability analysis. To refresh your memory, I can say, let me clarify. Von Neumann stability analysis is a analysis for numerical schemes to check whether how much stable it is, where we will be introducing a small errors and how it and we will check how the error is propagating. You can invoke your answers. Which of the following is best suited for von Neumann stability analysis? The answer is option C. Answer is option C. That is, von Neumann stability analysis can be applied to both linear value problems and periodic boundary conditions. Moving on to next question. Question number 5. Which of the following does not affect the stability of a hyperbolic problem? So, which among the following conditions won't affect the stability of a hyperbolic problem? First condition, mesh spacing, that is delta x. Second condition, velocity. Third condition, viscosity. Fourth condition, linear boundary value times the delta t. Options are option A, one only, first condition only. Option B, second and third condition. Option C, first and second condition. Option D, third condition only. So, which among the following conditions does not affect the stability of a hyperbolic problem? You can think and inbox your answers. So, which of the following does not affect the stability of a hyperbolic problem? Is it mesh spacing, velocity, viscosity, or linear boundary value times time? You can inbox your answers. The answer is option D, that is third condition only, that is viscosity only. So the question was on which of the following does not affect the stability. So all the other thing, that is the mesh spacing, velocity, delta t, all other thing can affect the stability of a hyperbolic problem, whereas viscosity doesn't have much say on the stability of a hyperbolic problem. Moving on to next question. If wiggles appear in a numerical solution, then what can be done to eliminate them? Conditions are: condition one, decrease the time step. Second condition, decrease grid spacing. Third one, use more accurate scheme. Options are: first condition only, option B, third condition only, option C, second condition only, option D, second and third condition. So suppose if wiggles appear in a numerical solution, how can how to eliminate them? What can we do to eliminate them? So we have seen in previous question what is wiggles. Wiggles are stable spatial oscillations. Stable spatial oscillations are called wiggles. So if wiggles appear in a numerical solution, how to eliminate them? You can inbox your answers. The answer is option C, decrease the grid spacing. That is, we have to uh, reduce the grid fusing, or delta x we have to reduce it. That is to refine the mesh. Next question. Which of the following method is not typically used for verifying the well posedness of a CFD solutions analytically? So we have discussed what is well posedness in the last week's lectures and interactive session. So here the question is on which of the following methods are not typically used for verifying well posedness of CFD solutions analytically. Options are option A, energy method, option B, Lyapunov function methods, option D, direct numerical simulations, option D, eigenvalue analysis. Question is actually easy question. So here, if you see, the question is on which of the methods are not used for verifying analytically. The question is on how analytically. If you concentrate on this particular part only, the question can be simply solved. So from below options, energy methods are analytical method, Lyapunov function methods are analytical methods, and eigenvalue analysis also analytical method. Whereas direct numerical simulation, that is DNS, is a numerical method. So the question is on not typically used for analytical solution. So this is a numerical method, or it is done for direct, it is done for numerical verification, not for the analytical assessment. So our answer is option C. Moving on to next question. Question 8. What is the difference between well posedness and ill conditionedness? So this basic question asking the difference between well posedness and ill conditionedness. Often these two terms has been misunderstood or uh, confused between each other. So for your understanding, uh, with your basic understanding, you can try to answer the question. What's the difference between well posedness and ill conditionedness in terms of a CFD or numerical analysis? Options are well posedness refers to the existence of a solution, while ill conditionedness refers to the difficulty of obtaining it numerically. Option B, there is no difference. They are the same concept. Option C, ill posedness is more severe condition than well posedness. Option D, well posedness only applies to steady state problems, while ill conditionedness applies to transient problems. So you can inbox your answer. You can try to solve the question and inbox your answers. What is the basic difference between well-posedness and ill-conditionedness? Our answer is option A. That is, well-posedness guarantees a solution exists, while ill-conditionedness indicates that the numerical solution might be sensitive to small changes of input data, making it difficult to obtain accurate results. So we have seen in last section that well-posedness is the ability of a system to have a unique solution which obeys initial values and boundary conditions. So that is a well-posedness. While ill-conditionedness is suppose our input value is delta x and our output variable is delta y. Suppose sorry, our input variable is x and output variable is y for simplicity. Then for a small delta x, the change in delta y is too large. Such a condition is called ill-conditionedness. So that is, if the system of linear equations are ill-conditioned, then the results can vary drastically for even small changes of input variables. So such a condition is called ill-conditionedness. So our answer is option A. Moving on to next question. You are simulating a laminar flow through a pipe using finite difference method. The discretization scheme is known to be consistent, but the initial condition for the velocity field is not smooth. What can you expect about the solution? So here the question is asking you to predict the solution for given initial condition. So the simulation is for laminar flow through a pipe, a simple problem using a finite difference method. and that it is said that the discretization scheme which is being used is consistent, but the initial condition is not smooth. So, what can you expect in the solution? Option A, the solution will converge to the exact solution as the grid size is defined. Option B, the solution will exhibit numerical oscillations even after grid refinement. Option C, the solution will be accurate but only for a limited time. Option D, the solution will not exist at all. So, which among the following can you expect for the above said system? You can inbox your answers. Our answer is option B. That is, the solution will exhibit numerical oscillation even after the grid is defined. Because the inconsistency between the initial condition and smoothness requirements of the scheme will lead to numerical oscillation. So mostly what we will think is like with grid refinement, our solution will be converged or we will get a good solution. But in these cases, what will happen is like if the initial condition is not smooth, then the scheme can lead to numerical oscillations, even if the scheme is consistent. Moving on to next question. When solving the Poisson equation for pressure in an incompressible flow, the pressure and the velocity fields are coupled through divergence constraint, that is delta U is equal to 0. Which method is used to enforce this constraint? Options are option A, direct substitution, option B, pressure correction method, option C, penalty method, option D, relaxation method. So when solving the Poisson equation for pressure in an incompressible flow, the pressure and velocity fields are coupled through the divergence constraint. Which method is commonly used to enforce this constraint? Options are direct substitution, option B, pressure correction method, option C, penalty method, option D, relaxation method. You can inbox your answers. You can try to answer the question. Answer is option B, that is pressure correction method. So in for incompressible flow, the pressure correction method is used for solving the Poisson equation for pressure. Here, what is happening is like in pressure correction method, the pressure is implemented. Pressure Poisson equation is implemented through pressure correction method where it iteratively solves for the pressure and velocity in the fields to satisfy the divergence constraint. Moving on to next question. For a transient heat problem, so it's a time dependent. For a transient heat problem, for a transient heat conduction problem, which scheme is generally preferred for capturing the sharp temperature fronts accurately? So the question here is like which scheme can capture the sharp temperature fronts while solving a transient heat conduction problem? Options are option A, forward difference scheme, option B, central difference scheme, option C, upwind scheme, option D, implicit Crank-Nicolson scheme. Our answer is option C, that is upwind scheme. So upwind scheme can incorporate information from the upwind direction, preserving the sharp fronts in the transient convection dominated problems. Whereas the central difference schemes might smear, that is, it will smudge the sharp edges, while the schemes like Rangel, which are implicit schemes, can have diffusion errors. So our answer is option C, that is upwind scheme. Moving on to next question. Consider a CFD simulation with a moving boundary. How does the movement affect the well-posedness of the problem? So the question is on how does well-posedness, how does the moving boundary affect the well-posedness of a problem? Options are option A, it has no impact as long as the governing equations remain the same. Option B, it can introduce additional challenges in specifying well-posed boundary conditions. Option C, moving boundaries always make problem ill-posed. Option D, moving boundaries only affect the accuracy of the solution and not the well-posedness. You can try to answer the question. For a CFD simulation involving moving boundary, how does the movement affect the well-posedness of the problem? Options are it has no impact as long as the governing equations remain same. Option B, it can reduce additional challenges in specifying well-posed boundary conditions. Option C, moving boundaries are always makes the problem ill-posed. Option D, moving boundaries only affect the accuracy, not the well-posedness. Our answer is option B, that it can reduce additional challenges in specifying well-posed boundary conditions. Because even though with moving boundary conditions, even if the governing equations stay the same, the movement or the moving boundary adds complexity to the boundary conditions. So these uh, boundary conditions has to be uh, formulated in such a way that it should not create some problem, um, creating the solution as making the system of equation lack a unique solution. Then it will be an ill-post condition. So that is we have to give considerations for framing special boundary conditions for the moving uh, boundaries. Next question. What is accuracy? Or accuracy refers to which among the following? Condition 1. How fast a scheme converges to the exact solution. Second condition. The difference between the numerical solution and exact solution. Third condition. The scheme's ability to preserve physical properties. Fourth condition. How sensitive the scheme is to small changes in initial conditions. Fifth condition, the scheme's stability to find the exact solution. So, which among the following does accuracy refers to? Options are conditions 1 and 2, option B, conditions 1, 2, and 3, option C, conditions 4 and 5, option D, all of them. You can try to answer the question. Answer is option C, that is conditions 4 and 5. That is, accuracy refers to how sensitive the scheme is to small changes in initial conditions. Also, the scheme's ability to find the exact solution. Mostly, this can be confusing, but it's strong since it refers to the difference between the numerical solution and exact solution. So, our answer is option C, that is statements 4 and 5. Next question. A scheme is called conservative if it is, options are, always converges to a solution regardless of initial conditions. Option B, preserve some physical quantity like example mass or energy over the time. Option C, guarantees a solution within specific bound. Option D, minimizes the error between steps. So, which among the following is best suited for conservative property? So, what's the explanation of conservative property among the options? You can try to answer the question. Answer is option B. That is, it should preserve the the physical quantities. That is the actual physical quantities that is there in our conservation equations, or our the quantities that are there in the physics should be conserved, or it should be preserved over the time. So that property is known as conservativeness. Next question. The next question is on the property boundedness. So boundedness ensures which of the following? Options are: option A, the numerical solution remains within a finite limit. Option B, the scheme always produces a unique solution. Option C, the error between the numerical and exact solution decreases with time. Option D, the scheme can handle large initial condition. So which among the following is meant by boundedness? Uh, the name itself gives away the idea, so it's easy for you to decipher. Try to answer the question. So um, the answer is option A, that the numerical solution should remain within a finite limit. So there should be an lower limit and upper limit for the numerical solution. So the property which ensures that our solution of the system of equations is kept within a finite limit. Such a property is called boundedness. Moving on to next question. Question is: a scheme is bounded if the solution values are. It's a different version of the previous question. A scheme is bounded if the solution values are: option A, remain close to the initial condition. Option B, never become negative or negative for positive initial values. Option C, approach a constant value as time increases. Option D, can be arbitrarily large depending on the scheme. How, what does it mean by a scheme is bounded? So our answer is option B. That is, it will never become negative for a initial value. So as we discussed in the last problem, boundedness means that the solution should be bounded to a lower limit and upper limit. So suppose this uh, initial value, that's the lower limit, or the initial value is on positive side. So that is, this is the lower limit. Somewhere here I am taking a value in the positive region. So this is the lower limit. So it going negative means it has to break this power limit. It has to go beyond the boundaries. So such a condition is called is uh, such a condition will never occur if the scheme is bounded. Moving on to the next question. A scheme is consistent if option A, it becomes exact as the discretization approaches zero. Option B, the error remains constant for all time steps. Option C, it produces a smooth and continuous solution. Option D, it is computationally efficient for large problems. So, what does it mean by consistency, or a scheme is consistent? So this question we have discussed in the earlier sessions also. The consistency is the property of the solution uh, approaching to the exact solution as the discretization or the grid spacing approaches to zero. So such a property is known as consistency. For a scheme to be consistent, it has to become the solution has to become exact as the discretization approaches the zero. Okay, moving on to next question. A scheme is stable if small errors in the initial conditions options are lead to large errors in the solution over time. Option B, do not significantly affect the final solution. Option C, remain constant through the simulation. Option D, grow exponentially with each time step. So the question is on stability. So for a scheme to be stable, how the initial conditions should be, or the errors in the initial condition, how the propagation of errors in the initial condition should happen for a scheme to be stable. Options are lead to large errors in solution over time. Option B, do not significantly affect the final solution. Option C, remain constant throughout the simulation. Option D, grow exponentially with each time step. So for a scheme to be stable, the small errors in the initial condition should not significantly affect the final solution. That is what is known as stability of the scheme. So the answer is option B, that the small errors should not significantly affect the final solution. Moving on to next question. A scheme is convergent if option A, it always produces the exact solution for any discretization. Option B, the error between the numerical and exact solution approaches zero as the discretization approaches zero. Option C, it is unconditionally stable for any step size. Option D, it requires minimal memory storage. So for a scheme to be convergent, which of the following options must satisfy? Answer is option B. That is the error between the numerical and exact solution approaches to zero. Next question. Which of the following statement about convergence is false? Option A. A convergence scheme approaches the exact solution as discretization size tends to zero. Option B. Convergence guarantee that the scheme will always produces a solution. Option C. A stable scheme is necessary condition for convergence but not sufficient. Option D. Non-convergent schemes can still be useful for qualitative analysis. So, which of the following is false regarding convergence of a scheme? Options are convergent scheme approaches the exact solution as the discretization size tends to zero. Option B, convergence guarantees that the scheme will always produce a solution. Option C, a stable scheme is necessary condition for convergence but not sufficient. Option D, non-convergent schemes can be still used for qualitative analysis. The answer is option B. That is, question is for finding false statement. So option B, that is convergence guarantees the scheme will have a solution. No, the convergence does not guarantee for a scheme to have a solution. Whereas uh, a stable scheme is necessary condition for convergence, but it is not sufficient for convergence. Also, non-convergent schemes can still be useful for qualitative analysis. So A, C, and D are true, whereas option B is false regarding convergence of a numerical scheme. Moving on to next question. The order of accuracy of a scheme refers to which among the following? Options are option A, the number of iterations needed to reach a desired solution. Option B, the rate at which the error between numerical and exact solution decreases with finer discretization. Option C, maximum error allowed in the simulation. Option D, computational complexity of the scheme. The question is on order of accuracy of the scheme. So, which among the following best suits for the term order of accuracy of a numerical scheme. Option A, number of iterations needed to reach a desired solution. Option B, the rate at which the error between numerical and exact solution decreases with finer discretization. Option C, maximum error allowed in a simulation. Option D, computational complexity of the scheme. We can try to answer the question. Our answer is option B, the rate at which the error between numerical and exact solution decreases with finer solution. That is the order of accuracy of a scheme. Moving to the next question. An unconditionally stable scheme for an explicit ODE, that is ordinary differential equation solver, guarantees which among the following? Options are: option A, the solution will always converge to the exact solution. Option B, the scheme is always accurate regardless of the time step. Option C, the solution will not grow unbounded regardless of the time step. Option D, the scheme is computationally efficient for all problems. So what does it mean to say unconditionally stable scheme or an explicit ODE? answer is option C. That for an unconditionally stable scheme, the solution will not grow unbounded regardless of the time step. So our right answer is option C. Moving on to the next question. In the context of numerical stability, what does it mean for a scheme to be unconditionally stable? So, so the same question or uh, different the same aspect of the numerical stability is asked in different context. What's the context of numerical stability? What does it mean for a scheme to be unconditionally stable? Options are option A, the scheme is stable for any time step delta t. Option B, the scheme is stable for a specific initial and boundary condition. Option C, the scheme is always accurate for any problem. Option D, the scheme converges to exact solution for any delta t. So, which among the following options is the numerical stability of a scheme to be unconditionally stable? The answer is option D. That is for for a scheme to be unconditionally stable, it means the scheme converges to exact solution for any delta t. So that's the meaning of unconditionally stable. Next question. Which of the following statement is true about which of the following statement is true about the relationship between consistency and stability? 1 minute. I think I made a mistake here. Yes. Option A is the right answer, not D. Sorry. When I got confused. Option A, that is the scheme is stable for any time step delta t. So this is the right answer. Next question. Which of the following statement is true about the relationship between consistency and stability? Options are: option A consistent scheme is always stable. Option B, a stable scheme is always consistent. Option C, consistency is necessary for convergence but not sufficient. Option D, both consistency and stability are necessary and sufficient for convergence. So the question is about the relationship between consistency and stability. Options are: a consistent scheme is always stable. Option B, a stable scheme is always consistent. Option C, a option C, consistency is necessary for convergence but not sufficient. Option D, both consistency and stability are necessary and sufficient for convergence. Our answer is option C. That is, consistency is necessary but not sufficient. Option C is our answer. Moving on to next question. While applying stability analysis, which of the following is not a typical approach? Options are option A, analyzing the amplification factor using von Neumann method. Option B, deriving the stability criterion based on physical properties of the equation. Option C, using graphical methods to visualize the behavior of numerical scheme. Option D, directly comparing the numerical solution with analytical solution for various time steps. So the question is on stability analysis. And for stability analysis, which of the following is not a typical approach? Options are option A, analyzing the amplification factor using von Neumann method. Option B, deriving the stability criterion based on physical properties of the equation. Option C, using graphical methods to visualize the behavior of numerical scheme. Option D, directly comparing the numerical solution with analytical solution for various time steps. You can try to answer the question. So, the answer is option D. That is, directly comparing the numerical solution is not used for stability analysis. It is not a typical approach. So, option D is our answer. Moving on to next question. Consider the following explicit finite difference scheme for the advection equation dou u by dou t plus c times dou u by dou x is equal to 0. Which condition guarantee the stability of the scheme? So the question is on stability of the scheme and said that explicit finite difference scheme is used for an advection equation. Options are option A, op, option A, C, that is this advection velocity, C, advection coefficient C, sorry, is greater than or equal to 0. Option B, C less than or equal to 1 by delta x, where delta x is the grid size. Option C, c square less than or equal to delta t by delta x the whole square, where delta t is the time step. Option D, the scheme is always unstable. So the question is asking for the condition that will guarantee the stability of the scheme. The options are option A, C greater than or equal to 0, where C is this one. Where C is that is C. So that option goes to C greater than or equal to 0. Option B, C less than or equal to 1 by delta x, where delta x is the grid size. Option C, C square is uh, less than or equal to delta t by delta x the whole square, where delta t is the time step and delta x is the grid size. Option D, the scheme is always unstable. Our answer is option D. That is, the scheme will always unstable. Moving on to next question. In the context of finite element methods, question is on finite element method, that is FEM. FEM. What does the term positive definite stiffness matrix imply for the stability of solution? So in the context of finite element method, what does the term positive definite matrix or positive definite stiffness matrix? Options are option A, solution is guaranteed to be unique. Option B, the solution is free from numerical oscillations. Option C, the error grows exponentially with time. Option D, the scheme is unconditionally stable. So which of the following implies stability for the solution in finite element method when positive definite when the stiffness matrix is positive definite. Our answer is option B, that the solution, if the stiffness matrix is positive definite, then the solution is free from numerical oscillations. So that's all for today. Thank you for joining. Thank you everyone.